So far, we have been talking about number systems, and especially the field of complex numbers. And we have been able to assign for each point in the plane a meaningful complex number. By meaningful, I mean that, okay, we can assign these numbers to the points of the plane in such a way that we can consistently add them, subtract them, multiply them, and for any non-zero number, you can divide them to each other. Okay? The thing is that when we were starting to building this number system, this was also, we were trying to some kind of solve polynomial equations, and we were trying to find, okay, when we are trying to say, for instance, x to the power of 2 plus 1 equal to 0, has a 0 or has a solution or not, can we really be sure that this kind of numbers exist in the field of complex numbers or not? Today we are actually going to talk about this. But the thing is that when we were also talking about this equation, x to the power of 2 plus 1 equal to 0, the problem of finding a solution for this equation turned out to be some kind of finding a square root for -1. Okay? And we can generalize this question and ask ourselves, if we want to calculate the square roots of, for instance, complex numbers, do they really exist? And if they exist, what are their forms? How can we find them? Because, as you know, for real numbers, only if they are positive real numbers, we can always find their nth roots, their square root, I don't know, cube root, and this kind of things. But what about complex numbers? Can we find this kind of roots for them or not? Which means that if we want to find square roots, let's start from here. If I have a complex number, which is given in this form, okay? When we are trying to find a complex root for it, which means that when we are looking for this kind of an object, how can we give meaning to it? We are some kind of trying to reverse engineer our way and say that, okay, let's assume that we have this w, which is in this form, x plus iy, and I don't know what it is yet, but I'm trying to some kind of say that, okay, if this is the square root of this number, which means that this w to the power of 2 must be equal to the z, then what should be my x and y in terms of this a and b? Okay? This is the meaning. If w satisfies this equation, it means that it's the square root for z, right? This is exactly the same meaning. So, having this a plus bi and this form, let's plug it into this and see what will happen. I need to write this x plus iy to the power of 2, and our z is going to be given in the form of a plus bi. Okay? Now, if we calculate this, what will happen? What is this complex number to the power of 2? We are just using this identity, right? A to the power of 2 plus b to the power of 2 plus 2ab. Okay, this is the identity that we need to use. Or you can also write this, multiply it itself, and just distribute it. So what will happen here? It will be x to the power of 2 minus y to the power of 2. Because this is squared means I to the power of 2, y to the power of 2, and I to the power of 2 is going to be -1. So we have this, plus I times 2 times the first one times second one. Second one is iy, and since I want to have this in a standard form, I'm just writing like here. This must be equal to a plus bi. I have this number a, I have this number b, and I do not have x and y, and I'm trying to some kind of find these values of x and y based on this a and b. Okay. What we see here is that we have two complex numbers that are equal to each other. So what should we do? When two complex numbers are equal to each other, when their real part is equal to each other, which means that this x to the power of 2. Are you going to be able to see it here? Okay, x to the power of 2 minus y to the power of 2 equals a. 2xy must be equal to b. Okay? This is a system of equations, and if we can solve it, then we are going to find the values of x and y based on this a and b. Okay? How can we solve this? You have seen many systems of linear equations, and you know this Gaussian elimination method and this kind of thing, but this is a nonlinear system. So we need to do some algebraic tricks in order to really find out what is happening. The thing that we are going to do, also let me call them 1 and 2, because we are going to use them. Okay. What I'm trying to do is this. If I do something to this expression, in order to have this x and y multiply to each other, then I can also plug b there and try to some kind of hope that we can find some way to get out of the situation. And one of the ways to do that is that if I take the power of 2 of both hand sides of this, then we are going to have this to the power of 2, this to the power of 2, plus 2 times this one, right? And we are going to have this x multiplied by y. So let's square both sides of this one. I'm using this dummy notation. So what is this x to the power of 2 minus y to the power of 2 to the power of 2? This is going to be x to the power of 4 plus y to the power of 4 minus 2 times x to the power of 2, y to the power of 2. Right? This is the left hand side of it. And what is the right hand side? It is a to the power of 2. Okay? One more thing. What do you see here? X and y multiply to each other, right? So some kind of I can use this. But if I directly use that, then I'm going to have this term x to the power of 4, y to the power of 4. And from a second degree equation, I have been raised myself into a first degree equation, which is a little bit harder to solve. So what we need to do is some kind of doing another trick. By another trick, I mean this. Can I write this expression in this form, x to the power of 2 plus y to the power of 2, the power of something, which, what will this be? This will be x to the power of 4, I have this, y to the power of 4, I have this, and from here, I will have 2x to the power of 2, y to the power of 2, right? But I need to have a minus 2 times x to the power of 2, y to the power of 2, and I have 2 of them more. So if I add here a minus 4 times x to the power of 2, y to the power of 2, then is this equal to this one or not? Yes, it is, right? So we have this. What will happen now? If you look at this, what is 4 times x to the power of 2, y to the power of 2?
P squared.
P squared, definitely. So I can take this to the other side, and I can write x to the power of 2 plus y to the power of 2 equal to, this is to the power of 2, but I'm just going to write it as, this is square root. Can I do it? I need to also maybe put a plus and minus here, right? But look at this. Is this a positive number or a negative number? This is always a positive number. And the square root of a positive number, which is a positive real number, right? Because A and B are real number, is always positive. So there is no need for me to select it with a minus or with a plus. This is just a positive number and we're done with it. Okay? Now I have a new equality. Let's call it 3. And let me add it here. X to the power of 2 plus y to the power of 2 equals square root of a to the power of 2 plus b to the power of 2. Okay. From here, can we find the values for x and y? this one and this one. If we add them together, what will happen? Minus y squared and y squared will cancel. So we will have 2 times x to the power of 2. Which means that, what is our x to the power of 2? Let me just clean here. Means that our x to the power of 2 will be equal to a plus square root of a to the power of 2 plus b to the power of 2 divided by 2. Okay? What about x? What can we say about x itself? For finding x, I need to just take the square root of this one, right? But look at this. Is this a positive number or a negative number? A to the power of 2 plus b to the power of 2 is always a positive number, and it is bigger than a. It is always bigger than a. So it doesn't matter if a is positive or negative. When you're adding this to that number, this is always going to be a positive number. So when you are taking this square root, this is something meaningful. Okay? But we are looking for some value, such that if we square it, what do we have? We have what this thing is inside of this, right? So the negative of that is also another solution for this x that I do not know it, right? So here I achieve actually for 2 solutions. One of them, let's call it x1, which is going to be this one. And I can also take another solution, which is going to be minus of this thing, right? So this is going to be a positive number, this is going to be a negative number. Fine? Okay. What about y? If we multiply this one by a negative and add them together, then again the same story holds, right? And we have, again, y to the power of 2 is going to be minus a plus square root of a to the power of 2 e to the power of 2 divided by 2. And from here, for y, I can get 2 values. One of them, which is this positive number. And is this really a positive number? Again, if a is negative, minus a is going to be positive, plus some positive number positive. If a is a positive number, minus a is negative. But since this one is bigger than this one, their summation, their addition is going to be a positive number. So this one is going to be a positive number, and I have this y2, which is going to be minus of y. Okay? What happened? We were having this number, and we were trying to find its square root. For instance, let's write an example. For instance, this 3 minus 2i. Okay? If we want to find these values of x1, x2, and this one, x2 for that number, which means that, can you please calculate the square root of this number? What are these values going to be for us? What is the value of a here? A is over 3, right? What is our b? Minus 2. So what is a to the power of 2 plus b to the power of 2? 9 plus 4, right? What is that going to be? Or can we work with some better number? Let's see, it doesn't matter, just numbers. So maybe I have some examples that I can give you. To have a perfect square, not true. Let's go with 4. Let's go with 4. Now I think we have cleaner numbers. Okay. What is a to the power of 2 plus b to the power of 2? 9 plus 16, which is 25, and that square root is going to be 5. So what is our x1? 5. A plus 3 plus 5, which is going to be 8, divided by 2, 4. Square root of 4, 2. So our x1 is 2, our x2 is minus 2. What about our y1 and y2? We have minus 3 plus 5, right? which is going to be 2 divided by 2. 1, square root of 1, 1. Which means that y1 is going to be 1 and minus 1. What was these values of x1 and x2 and y1 and y2? It was some kind of, you see, the values that we were looking for the square root, right? So if I want to write this value of the square root, what should I select from here? Can I say that, for instance, 2 plus I, x1 plus y1, I times y1, x1 y2, which means 2 minus I, x2 y1, minus 2 plus I, and minus 2 minus I. Can I say that all of these are square roots of a number? All 4 of them?
Minus 2 minus I be negative. The square root of.
Yes. The thing is this. When we are looking for square roots, we are some kind of solving this kind of an equation, right? A polynomial equation of degree 2. For instance, this equation is going to be z to the power of 2 minus 3 minus 4i equal to 0. We are trying to some kind of solve this polynomial equation. But how many roots do you expect to find for this polynomial? At most 2 of them, right? We will also talk about this. But anyhow, from high school material that you know. But you see, we have 4 options here. This means that we need to be very careful here about something, about selection of our numbers, this x1 and x2 and y1 and y2. We cannot select all of them. We have 2 options for this x values, 2 options for y values, which gives us 4 different values. But how can we really understand and really know that which one of them should we select? Let's go case by case. Let's go case by case. What is this equation 2? What does it mean if you look at this equation? X and y are multiplied to each other, and when multiplied by 2, we have this number b. So which means that when we are selecting that values of x1, y1 or whatsoever, we need to some kind of make use of this equation. Okay? How can we make use of this equation? Our b is a real number, which can either be positive, which can be 0, which can be negative, right? What will happen in these cases? If, for instance, b is positive, then what will happen to x and y? They must have the same signs, right? What if b is negative? They must have other signs, yes? This is exactly the way that we need to select this x1 and y1. But let's start first from here. When our b is equal to 0, what happens then? When our b is equal to 0, look at this. What do we have? A plus 0 times I, or a, which means that we are just calculating complex square root of a real number, right? We need to select these values. If b is equal to 0, what will happen to this term? A squared plus b squared, it's going to be square root of a squared, okay? What is the square root of a squared? A or minus a? If a is a negative number, then what will happen? This means that if you have this minus 4 to the power of 2, okay? We never say that this is going to be minus 4, right? We have minus 4 here because minus 4 is a negative number, and minus 2, sorry. Minus 4, no. And it's going to be 4. Okay? So we need to be careful about the sign of a, first of all. If a is positive, what will happen? If a is positive, then we have this square root of a squared equal to a itself. A plus a, 2a, divided by 2a, and the square root of a. So what is our x1? Square root of a. What is our x2? minus the square root of a. What is our y1 and y2? This was going to be a minus a plus a. 0 divided by 2, 0 and 0. So y1 and y2, they are both going to be equal to 0. So what happens? The case that b is 0 and a is positive, we are some kind of finding a positive real number is the square root, right? And we have these two solutions for it. Okay? But these are complex roots of a real number. What happens when our a is negative? What will happen here?
X will be.
This is, yes, exactly. E is already 0. Square root of a to the power of 2 is going to be minus a. It is plus a, 0. So x1 is 0, x2 is 0. x1 equal to x2 equal to 0. What will happen to our y1 and y2? This is going to be minus a divided by 2, which is going to be, y1 is going to be the square root of minus a. What is our y2? Minus the square root of minus a. Okay? And in this case, what is the complex root of a plus 0i when a is negative? X's are already 0. We need to place this value of y here, right? And it's going to be plus minus. From the formula, I have the I. I'm just writing the square root of minus a. Okay? And we are done with it. What will happen? What will happen if b is not positive? Not b is not positive, b is non-zero. Shall I clean here? Whenever b is non-zero, what will happen now? So which means that we have a complex number and not a real number. What will happen then? Our b is either positive, okay? And if b is positive, for x1 and y1 or x2 and y2, among them, what should I select? Based on this, I should select the values who have the same sign, which means that I need to select from here. If I'm selecting x1, which is a positive number, I need to also select y1, which means that one of the roots, let's call it w1, is going to be x1 plus I times y1. What about the other option? And if I'm selecting this one, which is a negative number, I need to also select this one, which is a negative number, which is going to be x2 plus y2, which I can write it as, what is x2? Minus x1. What is y2? Minus y1. And I can write this as x1 plus I times y1. Okay? So it is going to be positive, negative of x1 plus I y1. Okay? When b is negative, then what will happen? Our first root w1 is going to be, I need to select one value for x1, for x, which I'm going to select it as x1. And for the value of y, what should we select? Yes, y2, because they need to have different signs. I, y2, which I can write it as x1 minus I times y1. Right? What about w2? If for first one we have selected x1, we need to select x2. And from here, for value of y, what should we select? y1 plus I times y1. What was this x2? Yes, this is minus x1 plus iy1. And if you look at this, you see, it is going to be minus x1 minus I y1, which means that again we have this one with a negative sign. Okay? So W1 and W2 have positive negatives. Okay? Can we put all of these things in one single formula? Yes, of course we can. If we are calculating the complex square root of a plus bi, this is going to be plus minus of square root of a plus a to the power of 2 plus b to the power of 2 divided by 2. Am I going to write a plus here or a minus here? If you look at this, if b is positive, you're writing a positive. Okay? If b is negative, you're writing a negative sign here. So if I write here sign of b, is it going to be clear what's happening? Based on what is the sign of b? And if b was positive, what was the sign of b? We have defined it as positive 1. And if b was negative, we have defined it as minus 1. So we have it. Square root of minus a plus square root of a to the power of 2, b to the power of 2 divided by 2 multiplied by this I. Okay? And this is the square root of complex number. Okay? Can you please find the square root of 1 plus I? When we are writing this 1 divided by 2 or 1 divided by n whatsoever, we are just going to mean the set of all roots. So you need to here give me 2 values for it. Okay? Please calculate it. What do we have? I'm leaving it to you because it is just, some simplifications. But let's come back to this problem and decide about which one of them are the true values. Okay? So we have already calculated all of these things for these numbers. Okay? Which one of them are the true values? Which one of them should I select? 2 minus I. Why minus I? Why here you have a minus? Because of the sign of b, right? So it must be a negative 1. So we have this 2 and 1 with a negative 1. So we have this one. And the other solution or the other root is going to be minus of this number, right? Which one is it? Is minus 2 plus I, which is this one. Okay? So this one and this one are not the true. The problem now comes to this question. If we want to find the nth roots of complex numbers, how can we do it? If again we try to, like this, algebraically approach the problem, then we need to solve this x to the power of n, y to the power of n, a very huge algebraic problems, right? How can we make this much more cleaner? How can we change our perspective in such a way that the solution for finding the nth roots of complex numbers is much more easier? How can we do this? The trick is actually yes. How did we define the multiplication of complex numbers? Do you remember? It was some kind of adding the angles or the arguments of the numbers and then multiplying their distances from the origin. If I want to some kind of, if I have z here, okay, which has this angle theta and distance of r, if I want to geometrically find its second roots, which one of these points in the plane I should pick? First of all, what must be its length from the origin? How distance should it be from the origin? Because since I want to multiply that distance to itself in order to arrive to this r, I'm claiming that that distance must be square root of r. Which means that select the square root of r and all of these numbers that are here with a distance of the square root of r are eligible selections for me. Okay? But I need to also find this argument or the angle of this number which is making with the positive part of this real axis, right? What should that be? The question is this: when I'm multiplying the square root of z with itself in order to come to z, I need to do what? Add this angle to itself such that it turns out to be theta. So what should that angle be? Theta divided by 2, right? So what I'm claiming is this: if this angle is theta, if I select this one, this is going to be theta divided by 2. This number which is here is going to be square root of z. Why? Let's look at it. What is this square root of z's r, or distance from the origin? Square root of r, right? What is its theta? Theta divided by 2. What's this argument? It's theta divided by 2, okay? Now, if we want to multiply square root of z to itself, what is going to be its distance? Square root of r multiplied by square root of r, which is going to be r. Theta divided by 2 plus theta divided by 2, which is going to be theta, which is the distance and argument of this number. Okay? So you see geometrically what does it mean? It means that you need to just take the half of the angle and also do what? Take the square root of this distance. Okay? What else? But this one is giving us only one root, right? What about the second one? We have also seen that we have this plus minus of this number, right? So we are some kind of also rotating everything or reflecting it with respect to the origin. So question, can this number which is here, can it also be another value for the square root of z? Which means that if I add here the value of pi, which means that if I select this, is this also another solution or not? It is, right? Why? Because again, for this number, if you multiply the distance to itself, it is going to be r. And if you add these two angles to each other, it is going to be a one complete 2 pi. Then this theta divided by 2 is going to be doubled, which is going to be again theta. So we have also found another root, which is here. Okay? Can we extend this idea for finding higher order roots? For instance, the third root, fourth root, fifth root. How can we do this? The trick is that, yes, geometric way of looking at the complex numbers is really helpful for us. So, instead of writing them in the algebraic form, which we were saying that, okay, this z is going to be a plus bi, or let me write it as, since we have these coordinates, x plus iy. Okay? If I can represent this in the polar form, or this trigonometric form, then we are going to be able to find that roots easily, right? First of all, if I have this algebraic or a standard representation of a complex number, how can I turn this into these polar representations? How can I find this value of r, and how can I find this value of theta? And vice versa. If I have this value of r and theta, how can I come to this representation? Look at this triangle. In this triangle, if we want to calculate cosine of theta, what should we write? What should it be? X divided by r, right? From here, what can I say about the value of x? It is r times cosine of theta. Okay? What about sine of theta? It is y divided by r, which we can write it as r times sine of theta. Okay? What does this mean? If I have the distance of one complex number to origin, and if I have its argument, which we normally select this theta between minus pi and pi, okay? You can also add it. It is just going to rotate the same, but it is better always to select the value of theta in this. If we have this value of theta and r, we can find the values of x and y. But what about vice versa? If we have x and y, how can we find the value of r and theta? Of course. What is x to the power of 2? R to the power of 2, cosine to the power of 2. What is y to the power of 2? R to the power of 2, sin to the power of 2. If you add them, what will happen? This is going to be r to the power of 2, right? Or, what was the modulus of a complex number? It's distance from the origin, right? So you know also that this r is actually the modulus of this number. Which if you take the square root here, you will find that it is going to be exactly the same thing. What about theta? How can we find this value of theta based on x and y?
You know r, that we found it. You
Okay.
know y and x. So if you take the sine of it, you should find that.
We know the value of y. Yes, you're replacing it here, right? But what if you want to write a direct formula that calculates this theta based on the value of y and x? Divide these two to each other in a way that, for instance, if you want to calculate tangent of theta, what will it be?
X.
This one divided by this one, right? R's are going to cancel each other, and r is a non-zero number. So we are just going to have y divided by x. And from here, what do we have for the value of theta? Isn't it? This one divided by this one. R's cancel, sine divided by cosine is tangent. Okay. From here, we can say that our theta is going to be tangent inverse of y divided by x. Okay? A question for you. If we have this form for the number 1 plus I, can you write this representation of number, or actually what we have, this set which was going to be x plus iy. Now if we replace these values, and we have talked about it, it's going to be r times cosine of theta plus I times sin theta. Okay? 1 plus I. How can we represent it in this polar form? Can you please calculate it or find it out what's happening? What is the theta for this number? It is this one here, right? What is its angle? So theta is going to be what? Pi divided by 4, right? In radians, let's go. And what is its distance to the origin? It's square root of 1 to the power of 2 plus 1 to the power of 2, which is going to be square root of 2 cosine of pi divided by 4 plus I times sine of pi divided by 4. Okay? In order to not to write this cosine of theta plus I sine of theta, sometimes we write this notation, CIS of theta, in order to show this cosine of theta plus I times sine of theta. Okay? This is an abbreviation. So here I can write this as square root of 2 CIS of pi divided by 4. Okay? This is just an abbreviation.
What's CIS mean? What's that?
Cosine, I, sine. Okay?
Can you make that
Make which one? This? Şunu mu?
Okay.
What is the theta of this number? Look at it geometrically. 1, 1. So what is this angle?
Okay.
It is 45 degrees, right? Which is going to be pi divided by 4. Okay. If I want you to calculate this number, how can you do it? Question. Are we just going to multiply this 1 plus I 100 times to itself? Or can we geometrically also find a better way to calculate this? How can we do it? For a second, let me ask you this question. If we have, in this representation of complex number, this r equal to 1, what will happen then? I will be looking for all the complex numbers that have distance equal to 1 from the origin, right? You have a question or? Go on.
I think I know answer. Would be r would be r to the power of 100 and 100 times theta.
Why? First of all, we need to understand that, right? That's why we are trying to do this. If our r is equal to 1 here, we are just working with complex numbers whose distance to the origin are 1. And what are their representation? If I take any point from this circle, it is just going to be this CIS of theta, right? Or cosine of theta plus I sine of theta. Okay. Let's assume that this is our number. If I multiply this number to itself, which means that if I calculate this cosine of theta plus I sine of theta to the power of 2, geometrically, where will it go? Distance is 1, which is going to be multiplied by itself, which is going to be 1. So it means that the distance is going to be again 1, so it will be going to be here. Yes, and they're just going to add this angle to itself, right? So it is going to be theta plus theta, which is going to be maybe 2 theta. Okay? If I multiply this number 3 times to itself, what will happen? Again, distance is 1, but this time we will make it 1 time, 2 times, and 3 times, right? So what will be the argument of that number? 3 theta, right? What if we make it in inverse? Okay? Which means that if we take this to the power of minus 1, for instance, when we were doing that, we need to rotate this back, right? So it is going to be minus theta. If it's going to be minus 2, it is going to be minus 2 theta. And this, for any integer, this is going to work, right? This is a very important property of complex numbers, which also has a very special name to it, which is called the Unauthorised formula. Which states that cosine of theta plus I times sine of theta to the power of n is going to be cosine of n theta plus I times sine of n. Okay? Because geometrically we are just adding those things to each other. Question. If you place n equal to 2 in this equation, equality, what will happen then? What will be this side? Cosine of theta plus I times sine of theta to the power of 2, right? And the right hand side will be what? Cosine of 2 theta plus I times sine of 2 theta, okay? What is this number to the power of 2? Cosine to the power of 2 minus sine to the power of 2 plus I times 2 times first one times second one, right? Which is going to be 2 times sin theta plus theta, which is going to be cosine of 2 theta plus I times sine of 2 theta. We have two complex numbers which are equal to each other. What will happen then? Their real part must be equal to each other. So this one is equal to this one. And this one must be equal to this one. What does this mean then? We are some kind of recovering the formulas for cosine of 2 theta. What was cosine of 2 theta? Cosine is squared minus sine is squared. What was sine of 2 theta? 2 times sine times cosine, right? As an exercise for you, if you place n equal to 3, what will be cosine of 3 theta and sine of 3 theta? Okay? you look for this. Let me also check to find. Okay. Now that we have the Unauthorised formula, if we want to calculate, for instance, this number, how can we do it? If we are working with the standard representation of numbers, then it is going to be really complicated. We need to multiply this number 100 times to itself. But if we represent this number in this form, which is going to be square root of 2 times sinus of pi divided by 4, we can take this to the power of 100 very easily. How? This exponents come to the top of this one. The square root of 2 to the power of 100. It is going to be 2 to the power of 50. And it is going to be this number, which is going to be cosine of pi divided by 4 plus I times sine of pi divided by 4 to the power of 100. Based on the Unauthorised formula, what do we have here then? This is just going to be multiplied to the argument of cosine and to the argument of sine, which is going to be 2 to the 500 cosine of 100 pi divided by 4 plus I times sine of 100 pi divided by 4. Okay? What is this? Cosine of 25 pi, right? And what is that cosine of 25 pi? 2 pi, 2 pi, 2 pi. If you reduce it, it's going to be cosine of pi, which is going to be, what's cosine of pi? Minus 1. And sine of pi? 0. So it is going to be minus 1 plus 0 times I, which is minus 1 multiplied with this, it is going to be minus to the power of 50. Okay? By the way, this Unauthorised formula is going to help us to find the nth roots of complex numbers. How? Let's assume that we have this number z. Let me write it first here. Nth roots of. If you have a complex number which is represented in this form, cosine of theta 0 plus sine of theta 0. Okay? Something like this. How can we find its nth roots? Which means that, let's assume there is this number w, which is in this form again, cosine of theta plus I times sine of theta. And what we need to find is that we are trying to find the nth roots of this complex number, this one. Which means that if I take this w to the power of n, I need to have this equal to z. Okay? How is this true? Let's check it out. If I take this number to the power of n, what will happen? This is going to be r to the power of n. And this number to the power of n. What is this to the power of n? Cosine of n theta plus I sine of n theta, right? So it is going to be cosine of n theta plus I times sine of n theta. Okay? This must be equal to what? R0 cosine of theta 0 plus I times sine of theta 0. What do we have from here? We need these two to be equal, right? What will happen then? This must be equal to this one, which means that what is going to be our R? The nth root of R0. This is a positive real number, and for a positive real number, we have a uniquely assigned nth root, right? So this is something meaningful for us. What about the value of theta that we are looking to find it based on this value of theta 0? How can we find it? This one must be equal to this one. This one must be equal to this one, right? Or when these equalities are true, then n theta is equal to theta 0 plus integer multiples of 2 pi, which is going to be 2 pi k for k and integer. Okay? Now, From here, what is our theta? We are looking for theta, right? What will that be? Our theta is going to be theta 0 divided by n plus divided by n. Now, how many different arguments do we have here? Or how many different angles? It seems that since this k is changing, we are going to get infinitely many different roots for a complex number, right? But is it really true? After some point, if this k is equal to n, it will be cancelled, and cosine of some angle plus 2 pi is again going to be cosine of that angle. So we are going to be in this periodic movement, and we are going to come back to where we have started already. So for how many values of k we have different angles? When k is 0, 1, 2, up to n minus 1. Okay? What does this mean then? For a complex number, when we are trying to find its nth root, we are going to always find n different values. Why? Can you geometrically interpret this?
Could it also be n plus 1 and plus 2 plus 1?
What?
Could it surpass n?
Yes, it can be.
Why
But when it is n, if it is n, again we are at this one, right? 0. If it is n plus 1, it is again the same as putting k equal to 1. So it is going to be the same thing. But for these values, we are going to get different distinct values. Okay? So remember this. This is very important. N distinct roots. Okay? For instance, if I ask you to calculate the square root of this number, which means that 1 plus I to the power of 1 over 2, what will happen? What? Yes, of course. Because in this, we have already used the standard form and calculated it. But since we have also this polar representation, let's also continue with this and see where it will lead us. What will happen to this then? We need to take two values, right? What are these two values? The distance of it from the origin must be the square root of this one, which will be what? Square root of 2. And what is going to be its angles? If this is our r, what is our theta? It is going to be theta 0, which is here what? Pi divided by 4. It is going to be pi divided by 4, divided by which roots I'm looking for? The square roots, right? N is equal to, I have to divide this by 2 plus 2 pi k divided by 2 for values of k, 0 and 1. Okay? So what is these two values for the square root of this 1 plus I? First root of 2, CIS of pi divided by 8. If k is 0, we have nothing here. And the other one is, this is also the fourth root, sorry, square root of 2. CIS of pi divided by 8 plus what? Yes. If you turn this into the standard form, you will see that they are going to be exactly the same numbers with what we have calculated with that long square roots of a plus square root of a to the power of 2 plus b2 and this kind of things. What is our R0? square root of 2. What is our theta 0?
3 divided by 4.
Pi divided by 4. And since I'm trying to find the third root, what is our n? 3, right? Okay. Let me not try to write that. And n is 3. Okay. If we are trying to find r, if we are trying to find this r, what should we do? We were taking the nth root of this r0, right? So our r is going to be third root of the square root of 2, which is what?
2 raised to power plus 6. 2 raised to power plus 6.
Yes, or the sixth root of 2, right?
Yeah.
If our theta 0 is our pi divided by 4, what are the values of theta?
3 pi over 2.
We have t0 divided by 3 plus divided by 3. For which values of k? 0, 1, and 2.
Yeah.
Okay?
So, theta
Pi divided by 4 divided by 3, which is pi divided by 12. And we have the first root is going to be this one, cosine of or CIS of pi divided by 12. Instead of k, if you write 0, what will happen? Just pi divided by 12. The second one is going to be 6 root of 2 CIS of pi divided by 12 plus, instead of k, we need to write 1, which is going to be 2 pi divided by 3. What is the third one?
CIS
Pi divided by 12 plus
4
4 pi divided by 3. Okay? We have these three values. Another question to ask. Let's come back to this point. Again, go back to understanding the things geometrically. When we are, for instance, calculating the third root of this one, what is happening?
What?
Geometrically, what is happening, I'm saying? When this is 1 plus I,
On the
okay,
second, on the other.
we are finding one of these complex roots, which is going to be this distance and this angle divided by 3, which is going to be someplace here, right?
Yeah.
What will happen to other two? The other two are rotations of this number. How much rotations? 2 pi divided by 3, right? We are just rotating them 2 pi divided by 3 pi. So it is going to be in this circle, it is going to be rotated. Maybe it's going to come here. The other one is going to come here, okay? So we have this kind of a structure. So if we know one of the roots, for finding the other ones, we just need to rotate them, right?
Yeah.
This brings us to a very important thing, which is called the nth roots of unity. When we are doing this rotation, which one of the things are that just rotates? If you multiply a complex number to which complex number, it will just rotate it and not scale it. All the complex numbers whose lengths from the origin or their distance from origin are equal to 1, right? And if we do this kind of things, they will just rotate these complex numbers. And if we want to regularly rotate all of those things in order to find all the roots, we need to be able to find the nth roots of number 1. So, nth roots of unity. Here by unity we mean number 1. Which means that if we want to find the nth roots of nth complex roots of number 1, What should we do and how we can find them? Again, we need to represent this in the polar form. Okay. What is the polar form representation of number 1? It is just CIS of 0, right? Cosine of 0 plus I times sine of 0. So for 1, what is its R0? 1. What is its theta 0? 0. Now, if we want to find this roots, what should we do? We again need to write the same formula, right? So, what is the complete set of nth roots of 1? What they are going to be? They are going to be nth root of 1. What is nth root of 1? 1. It is going to be CIS of 0 divided by n plus 2 pi k divided by n for values of k being from 0 up to n minus 1. And what is this? This is going to be cosine of 2 pi divided by n plus I times sine of k divided by n. Okay? If our n is equal to 2, if we want to find the second roots of 1, what will happen? What will happen if we do this? Let's go with n equal to 2. And if we want to find the square root of 1, what will happen? We will select this n equal to 2, and our k will be 0 and 1. If our k is 0, what will happen? It is going to be CIS of 0, and what is that? Cosine of 0 plus I times sine of 0, which is going to be 1. What is the second value? We are just going to replace k with 1 and with 2, right? This is going to be pi. What is cosine of pi? Minus 1 plus I times 0, which is 0, so it is going to be 1 and minus 1. Geometrically, where they are? Here and here. Okay? Two different complex roots. What about the case that n is equal to 3? What is the third roots of 1? We are just going to select this n equal to 3 and place the values of k equal to 0, 1 and 2. If we place the value of k equal to 0, again it is going to be 1, the first one. What about the second one? Cosine of 2 pi 1 divided by 3, which is cosine of 2 pi divided by 3. Plus I times sine of 2 pi divided by 3. Let me write it as the CIS of 2 pi 3. Okay? What is this number actually? You have it here, right? In this, here is 2 pi divided by 3, and it is this number. Okay? What is this equal to? Minus 1 divided by 2 plus square root of 3 divided by 2 times I. Okay? What about the other one? Again, we need to rotate this, an additional 2 pi divided by 3. Or here, instead of k, we need to write 2, which is going to be CIS of 4 pi divided by 3, which is going to be at this point. Okay, with this, here is also 2 pi divided by 3, which is going to be minus 1 over 2 minus the square root of 3 divided by 2 times I. Okay? Clear? What about the fourth roots? If you consider this, you will see that, okay, what is happening is that the third roots are actually the vertices of a triangle which are living on top of this unit circle, and one vertex is on this point 1. So we have this kind of figure. If you want to place the force roots, for instance, what will happen? Force roots will also leave here, but this time on top of a regular foregon. And it is going to be a square, right? And one of the vertices we should place in this one. So they are going to be leaving here, at this point, at this point, at this point. So which means that if you take the force roots of 1, you will see that it is going to be 1, I, minus 1, and minus I. 4 different roots. Okay? And for any other complex number that you want to, for instance, calculate the force roots, just find one of them. Then multiply them by these numbers. And you will have the whole set of these complex roots. Please go on. Okay, what?
How did you convert CIS to pi over d to its x and y component?
What is CIS of 2 pi divided by 3? This is cosine of 2 pi divided by 3 plus I times sine of 2 pi divided by 3, right?
Yeah.
This is x plus I times y. What is cosine of 2 pi divided by 3? What is cosine of 120 degrees? Minus cosine of 30 degrees, right? Which is going to be minus 1 over 2. Instead of every time just writing minus 1 over 2. Plus I times, what is sine of 2 pi divided by 3? Again, sine of 120 degrees. Which is going to be square root of 3 divided by 2. Just calculating this complex trigonometric values for cosine and sine. Okay? Is it clear? One other thing that I need to say to you, when we are selecting this k equal to 1, okay? This CIS of 2 pi divided by n, or the first one after one that is coming with a positive angle, we normally show it with this W index n, or omega n, okay? Which means that the nth roots of unity. If you want to find the second one, this is going to be multiplied to itself. So it is going to be Wn or omega n to the power of 2. If you want to find the third value for the nth roots, then it is going to be this one multiplied to itself 3 times, or Wn to the power of 3, and so on and so on and so on. Okay? So for instance, this is 1, this is W3, this is W3 to the power of 2. Okay? This is also a notation that you need to keep in mind. Fine? Okay. Shall I give you another example? What should I give you? Do you want to solve another example for yourself? Okay. Please write down the fifth roots of unity. What are fifth roots of unity? Write it down explicitly, and can you also please show it on this argon diagram? Where are they leaving? Okay. One more thing that we need to discuss is that Euler's formula. We haven't yet talked about infinite series and Taylor series expansion of functions. But assuming that it is going to be clear what's happening, we define this exponential of a complex number e to the power of z with this notation: summation of all of these z to the power of n divided by n factorial. Then n is running from 0 up to infinity on the set of natural numbers. Okay? So this is going to be, if I place instead of n, 0. By the way, do you know what is n factorial? We define 0 factorial and 1 factorial equal to 1. Okay? And for n greater than 1, we define n factorial to be n times n minus 1 factorial. It is a recursive definition. For instance, what is 4 factorial? It is 4 times 3 factorial. And what is 3 factorial? 3 times 2 factorial. What is 2 factorial? 2 times 1 factorial. So it is some kind of multiplication, the number up until 1. Okay. If you have this, and we are just going to sum all of these values. If I write this explicitly, what should I write? I need to place n equal to 0. What is going to be? Z to the power of 0, which is 1, divided by 0 factorial, which is again 1. So it's going to be 1. Plus, this summation means that you're just going to add all of these things when this value of n is changing. If you place n equal to 1, what will happen? Z to the power of 1 factorial, which is going to be z. If you place 2, it is going to be z to the power of 2 divided by 2 factorial. So it is going to be z to the power of 2, 2 factorial, z to the power of 3, 3 factorial, plus z to the power of 4, 4 factorial, and the rest. We are going to show that this is actually something meaningful. No matter what you place in place of z, it is always going to be something meaningful. This is a convergence series, actually, but we are going to talk about it. Anyhow, if you have this, and this works for all of the complex numbers, let's take this I theta, okay, or Ix, or whatsoever you would like to have. If you place I theta in both hand sides of this, what we are going to get, this is going to be e to the power of I theta. Okay? What will happen here? It is going to be 1 plus I theta. What is z to the power of 2 when z is I theta? I to the power of 2, I squared, theta squared. What is I squared? Minus 1. So it is going to be minus theta squared divided by 2 factorial. If we place I theta here, what will happen? I cubed. What is I cubed? I to the power of 2 minus I, exactly. Minus I times theta to the power of 3, 3 factorial. If you place it here, I. Not I. No. 1. It is going to be theta to the power of 4, 4 factorial, and the rest. No. This is a complex number, right? What is the real part of this complex number? So if I want to write this in the standard form, I need to write its real part plus its imaginary part, right? The real part of this number is the part that does not have any i's. Right? This is also part of its real part, right? So this is going to be 1 minus theta squared 2 squared. This does not have, I'm just writing it, theta to the power of 4, 4 factorial plus the rest. Plus, so this is the real part of this number. What about its imaginary part? Which means all of the numbers that are multiplied by this I. We have this theta. We have what? Theta to the power of 3, 3 factorial. Theta to the power of 5, 5 factorial, and the rest. Okay? If you are a little bit careful, we are going to see that. Like this kind of series expansion. What has happened here for the e to the power of z? If we want to write the Taylor series expansion for the function cosine, this is its expansion. So this is actually cosine of theta plus I times. And you will see that this is actually the Taylor series expansion for sine, yes. So it is sin theta. So in general, what we have is this. E to the power of I theta is going to be cos theta plus I sin theta. Okay? Good? What was the numbers cosine of theta plus I sine of theta? As theta were changing, there were all of the numbers who were living inside this unit circle, right? Distance 1. So any complex number which lives on this circle, it it also has this e to the power of I theta form of representation as well. Any complex number, you could write it as what? Cosine of theta plus I times sine of theta, right? Now, instead of this, if I write e to the power of I theta, I can show all of the complex numbers in this form as well. It's called the exponential form of complex numbers. Okay? In this form, if we want to multiply two complex numbers or take their exponents and so on, what will happen? If our z is r1 to the power of I theta 1, if our z2 is r2 e to the power of I theta 2, what is z1? z1 plus z2 is just this number plus this number. There is nothing beautiful and compact over there to put it all together. But what is z1 times z2? We are just going to multiply their r1 and r2 values. So it's going to be r1, r2. This is going to be e to the power of I theta multiplied by e to the power of I theta 2. E to the power of I theta 1 plus. Which you can write this as r1, r2 e to the power of I times, just add these two, right? Fine? If r is equal to 1, e to the power of I theta 1 is a number on the unit circle. But for all other complex numbers, we can also have this representation. Just have its argument and just find its distance from the origin. So you will have that representation for the complex number. What we are writing here, this is exactly the same thing. There's no difference between them. We are just changing our notations. That's all. What is z1 divided by z2 in this notation? It is going to be r1 divided by r2 e to the power of I theta 1 minus theta 2. Right? We're dividing them and we're assuming that the values of exponentials are the same. The laws are true. Okay, good. If here, in place of theta, this argument that we have, you pick the number pi, what will happen? E to the power of I theta is cosine of, or CIS of theta. Okay, minus 1. If we select theta as pi, what will happen to the left hand side, first of all? It's going to be e to the power of I pi, right? What is this? Cosine of pi, which is minus 1 plus I times 0, which is, if you take this to this side, it is going to be this formula, which they call it the most beautiful formula in mathematics. Why? Because all of the five most useful numbers in mathematics that appear everywhere, you can see them all here. A gathering of numbers. Okay? This e is the exponential thing, or it is the base of the natural logarithm. This number 2.17, the rest. I is the imaginary unit. Pi is this pi. The ratio of circumference of a circle divided by its diameter. Multiplicative unity, multiplicative identity, and additive identity. You have all of them all together. Okay? Now, we are almost done with what we needed to cover. There are a few things that we need to talk about, is finding the roots of complex numbers. Not only that, but finding the roots of a polynomial equation, for instance, of degree 2, degree 3. If you have quadratic equations, if you have cubic equations, and if you have equations of higher degrees, can we always find roots for this kind of equations or not? So what I'm asking is this. When we were building the set of real numbers, we came up with an equation, x to the power of 2 plus 1 equal to 0, which did not have any solutions in the set of real numbers. But what about any other equation? Can you write an equation with complex coefficients, a polynomial equation with complex coefficients, such that we can never find any root for it in the set of complex numbers? Which means that, are there any polynomial equations such that if we want to find roots for them and solve them, we need to extend this world from complex numbers to bigger number systems or not. This is the concept of fundamental theorem of algebra. And over there, we are actually saying that no. In the field of complex numbers, or in the set of complex numbers, it doesn't matter. This addition, we don't care about the order. The field of complex numbers is algebraically closed, which means that for any polynomial equation with complex coefficients that we can write, we can always find roots in the set of complex numbers. So there is no need for us to go beyond complex numbers. So our story of building these number systems finally come to end here. Okay? If we have a linear equation such that the coefficients are complex numbers and the coefficient of this z is not equal to 0. Okay? What is the solution of this linear equation? Can we write this as minus b divided by a? B is a complex number, a is a complex number. And we have a unique solution for this, right? It is always going to be like this. For instance, if you have 2 plus I times z plus I equal to 0. Can you please solve this equation? What is the solution of that linear equation? Yes, RZ here is going to be minus I divided by 2 plus I. And if you want to write this in the standard form, how can we divide these two complex numbers to each other?
2 minus I.
Just multiply this with the conjugate of this denominator, right? 2 minus I, 2 minus I. This is 1 actually, and multiplying a number with 1 does not change it, so you have it. It is going to be what? Minus I times 2, minus 2I, minus I times minus I, plus I squared, which is minus 1, divided by, what is this? The modulus of this one, or 2 to the power of 2 plus I to the power of 2, which is minus 1, which is going to be 4 minus 1, 3, right? So this is going to be minus 1 over 3 plus minus 2 times I, or minus 2I. Okay? So for any linear equation, we can always find a unique solution for it. Okay? What happens if we have quadratic equations, which means that equations of this form? Yes, this must be 5, sorry. This is going to be minus 1 divided by 5, minus 2 divided by 5. I have it in both of them here. Yes? Fine? What if you have quadratic equations? What are the general form of it? When we have a quadratic equation, we mean an equation that it has degree of 2, which means an equation like this. Az to the power of 2 plus Ez plus c equal to 0. This coefficient, we are taking it non-zero, because if it is 0, then this is just a linear equation, right? Yeah. And all of these coefficients are complex numbers. Okay? How can we solve this equation? The thing is that this is a complex number, and all of them are complex numbers. So you cannot interpret this as a, you need to have, if you look at this function as a function, if you take this f of z as a z to the power of 2 plus ez plus c, this is actually a function from the set of complex numbers to set of complex numbers. Domain is a plane, codomain is a plane, okay? So if you want to show the graph of this, we need to have 2 dimensions times 2 dimensions, which is going to be a 4-dimensional space, and we are not able to do this. So this is not a parabola, some kind of. It is, but it is not. Anyhow, how can we solve this equation?
Can you use the quadratic formula?
Yes, what is that quadratic formula and from where it is coming?
Discriminant.
What is that discriminant? How can we get it?
The root.
The root of what? Let him continue and I will come to it. What is your name, by the way? Can you please?
Vadim.
Vadim.
Yes.
Please, Vadim.
So we need to find discriminant.
But what is discriminant of this equation? And when you are saying that, okay, we need to find discriminant,
B in second grade, like in power, second power.
okay,
Minus 4 multiplied by.
4AC, right? Okay.
by
But
A,
why this formula? Why not some other formula?
And then we should do minus B plus or minus the square
Okay.
of discriminant divided by 2 divided.
Yes, but why you are using this formula?
Well,
This is to check whether
the
the
quadratic
roots are
equation
imaginary.
be like same.
Yes, of course. This is a quadratic equation. We know about it. And you have this formula for minus b plus minus the square root of delta divided by 2a. But from where that equation is coming? When you're writing that formula, from where it is coming? Did we just memorize it, or is there a reason that we are using that formula? This is the thing that we are going to discuss, actually, right?
Quadratic, the root.
Yes, we will discuss it. Abigail, you also had something to say, right? Your hand was raised, so solved? Okay. The trick for finding the roots of a quadratic equation is by completing the square. What do we mean by completing the square? First of all, we always like to work with equations such that the coefficients of highest degree is equal to 1. Okay, and since this a is not equal to 0, we can divide both hand sides with a, and we can write this equation in this form. Z to the power of 2 plus BAZ plus CA equal to 0. Okay? By completing the square, what we mean is this. I need to have this term, okay, in such a way that we only have one Z. How can we do this? What is the half of this? B divided by 2a, right?
Yeah.
Z plus. If I take this to the power of 2, what will happen? This will be Z to the power of 2, which I have it here. It will be 2 times the first one times second one. And what will that be? 2 times Z times B divided by 2a. It is going to be B divided by a times Z, which means that I have also this one. And what we will have as an extra, this b to the power of 2 divided by 4a to the power of 2. Do we have it here? No, we do not have it here. So we need to just get rid of it. Half by writing it like this. So what is this? Let's go over it again. This is going to be z to the power of 2 plus BAZ plus b to the power of 2 for a2 with this minus b to the power of 2 for a2. These are going to cancel. And what is this whole thing? It is this one. Right? And what do I need to add also? This c plus a. Fine? If I take everything to the right hand side, what do I have here? Some complex number is squared equal to some other complex number, right? Is this something like finding the square roots of a complex number or not? So it seems that it is going to be helpful for us. So, z plus b divided by 2a to the power of 2 is going to be what? If you take everything to the right hand side and take this denominators, multiplying this by 4a and again by 4a. So we have the same roots. This is going to be what? 4a squared b squared minus 4ac. Do you see from where this b to the power of 2 minus 4ac is coming? Now, I want to get just this one because we are going to call this delta. So if I multiply both hand sides of this equality with this 4a squared, can I write this as 2az plus b to the power of 2 equal to delta, where our delta is going to be b to the power of 2 minus 4ac. This is what? 2a to the power of 2, right? If I multiply by both hand sides, this is going to cancel out and 2a is going to be multiplied inside of this. So is it clear? Any questions? Is it unclear or clear? Clear, right? Do you have any questions? Okay. Now we have this. Look at this. If we want to find only this place, because we are trying to some kind of find z, right? What should I do in order to get rid of this 2 and find this and do the rest? We are just going to take the complex square roots of this side, right? By the way, why this thing is called a discriminant? If it is equal to 0, as you know it, then we only have roots that are equal to each other. This means that we cannot discriminate between roots. They are the same roots. But when it is non-zero, we can discriminate between roots, which means that we can say that, okay, these two roots are different from each other. Okay? That is why it is called discriminant, because it discriminates between the roots. Anyhow, if we take complex square roots of both hand sides, what do we have? 2az plus b equal to square root of this delta. And this is the complex square root actually. Okay? From here, what is our z? Minus b plus square root of delta divided by what? 2a. Okay. How many roots do you see here? 1 or 2? Where is the second one?
There's a negative one.
No, not plus, minus. I have just written it as a plus. But I'm claiming that we actually see 2 roots over there. Why? Because as we have calculated, a square root of a complex number, how many values did we have for it? 2 values, right? So when we are taking complex square root of a complex number, this is actually 2 numbers. Okay? And it was plus minus of this or whatsoever. Here it means that this is going to be 2 values actually. Plus minus of, let's call it W12 for instance, okay? Actually this is 2 numbers, which means that we have 2 different values for our roots, okay? An example. Z to the power of 2 plus 2 plus I z plus 2 minus 2I equal to 0. Can you please solve this equation? Can we here claim that if our delta is positive, then we have 2 different roots? If delta is negative, can we even claim or talk about this kind of positivity or negativity of our delta?
You can't take a square root of a negative number.
We can take a square root of the negative numbers, but the thing is that, as you have proved in your exercises, right? The field of complex numbers is not an ordered field. So you cannot say that this complex number is a positive number, this complex number is a negative number. And since this delta is a complex number here, we can never say that, okay, if it is positive, this will happen. If it is negative, that will happen. It doesn't matter for us. It is completely meaningless for us to say that, okay, if this is positive, then we have 2 read roots. If this is negative, it is completely meaningless. We only have non-zero complex numbers, zero complex numbers. If this delta is 0, the complex number 0, then 2 roots are the same. Okay? We cannot discriminate between these 2 roots. But when it is not equal to 0, since every non-zero complex number have 2 distinct roots, we actually have 2 values for this and we have 2 different roots. But talking about positivity or negativity of delta here is meaningless, because the field of complex numbers cannot be ordered. First of all, if we want to solve this, we need to find this delta and place it here, right? What is our A here? First of all, 1. What is our B? 2 plus I. What is our C? 2 minus 2I. Okay? What is our delta? B squared minus 4AC, which is going to be equal to what? 2 plus I squared minus 4 times 1 times this, minus 4 times 2 minus 2I. Okay? What is this equal to? This is going to be 4 I squared, which is minus 1. 4 minus 1, 3. 2 times first one times second one, which is going to be 4I. Okay? What is this? Minus 8 plus 8I, which is going to be minus 5 plus 12I. Okay? Now, in order to find these roots, we need to calculate the square root of this delta, right? So, what is the square root of minus 5 plus 12I?
Can you put it 5 up?
Yes, you can have 2 approaches. You can have 2 approaches. You need to find R or theta, okay, and find that formulas that we have already used for finding the second roots. Or you also had this explicit formula, right? Plus minus of, yes, exactly. Let me write it there. Plus minus of, what do I have? The square root of A. Our A here is what? Minus 5. Plus square root of?
That's 25.
5 to the power of 2. 12 to the power of 2. And what is their summation? 169. Which this square is going to be, well, let me write it.
Square root of 69.
Which is 13, right?
Yeah.
So this is going to be 13. Divided by 2 plus, what do I need to write for the next? Sine of this B. What is sine of B?
Positive.
Positive, so it is going to be positive really. Square root of what? Minus A, which is going to be minus 5,
Yeah,
which is going to be 5 plus 13 divided by 2 multiplied by this I. Okay? Can we make this simpler? Yes, of course. It is going to be plus minus of what? Minus 5 plus 13. 8 divided by 2. Square root of 4. So this is 2 plus 5 plus 13. 18 divided by 2. 9. Square root of 9. 3. Okay? So we have 2 values for it. 2 plus 3i minus 2 minus 3i. Okay? So what will be our roots? What is going to be our z1? It is going to be minus b, which is going to be minus 2 plus I plus one of these, 2 2 plus 3i divided by 2a, which is 2. And our second root is going to be minus 2 plus I minus of 2 plus 3i divided by 2. Can you make the simplifications and let me know of solutions? Am I writing smaller or?
First one is I.
First one is I.
First one is I. Second one is
Minus 2 times I.
minus 2 minus 2 times I. Do you agree with this? Okay, now question. Can you check that these are really the solutions? Which means that can you take this I, plug it here in place of Z, and see that it is equal to 0? And also please do it for this number. Let's check it. What is the next step in our journey of solving equations? Cubic equation. A is to the power of 2 plus. Let's take this directly as 1. Go back to this. A, B, C. A, B, and C are complex numbers. Okay. If we have a cubic equation, how can we solve it?
Cardano.
Cardano's formula, right? Who was it? What did it? Was it? Okay. How can we derive Cardano's formula?
It's very long.
This is exactly what we are going to do right now. We are some kind of trying to find out about this Cardano's formula. The method of finding the solutions for this equation is some kind of a rabbit out of hat. So there is a lot of tricks, and we need to do a lot of things in order to find the roots. And people have been working on this problem of finding a general formula to solve the cubic equation for many, many years. The first person who had been able to come with this formula was actually Tartaglia. He was an Italian mathematician. He has told this formula to Cardano and asked to never publish it and to vow to never publish it and this kind of things. But Cardano actually published it. And because of its publication, this formula is known in the name of Cardano. But what is it really? And how can we use it in order to solve this kind of cubic equations? The first thing that we normally do is called the Schoenhaus transformation. Schoenhaus transformation. Which kind of makes this z to the power of 2 to disappear. Okay? And how can we do it? We are just going to take z equal to t minus a divided by 3. Okay? Can you please replace this in this equation and find out the general form of the reduced equation? Z küpün önünde çarpan var. We have a coefficient here, but we can divide everything to that since it is non-zero. If it is 0, then this is already gone, and we have a quadratic equation. And if it is non-zero, since we want to work with this thing being 1, divide everything to that, and call this A, call this B, call this C. Okay? If you replace this here, or do this Schoenhaus transformation on this equation, you will see that it is going to turn into this form. T to the power of 3 plus pt plus q equal to 0. Okay? We normally turn our equation into this kind of an equation and then solve it. Okay? Why we are doing this, first of all, again, it is just a bag of tricks. That is why they don't teach it in the high school. Because everyone is asking why this is coming, why we are doing this, and why this kind of things. But people have been working on this kind of tricks many, many years in order to be able to finally crack the way to solve this equation. Anyhow, the next thing that you're going to take is that let's assume this solution T is going to become in this form. One number plus another number in terms of u plus v. Why we are taking it like this? Because it is some tricks. We have been trying many different tricks. They haven't been working, but this one has worked. That is why. If we place this here in this equation, what we are going to get? U plus v to the power of 3, which is going to be what? U to the power of 3 plus v to the power of 3 plus 3 times u squared v plus u v squared. Okay? Can I take a factor of 3uv in these terms? I can. And if I do it, what will happen? 3uv times u plus v. Okay? This is only for this one. Plus p times u plus v plus q equal to 0. Okay? Now look at this. This term and this term are common in both of them. If we take a factor out of it, what will happen? How can I write this? Can I write this as 3uv plus p multiplied by u plus v? And if I want to check it, just take it, distribute it. U plus v multiplied by this one is 3uv multiplied by u plus v plus u plus v times p. Okay? If we are going to accept this as it is, then the thing is that for this kind of u and v, we can find many, many different solutions, right? If I give you a number and I ask you to write it as summation of two numbers, you can always find many different representations. Okay? Çok teşekkür ederim kapıyı kapattığınız için, sağ olasınız. But if we impose another restriction on them, then we hope that we are going to find a unique set of u and v that we can put like this. What is that restriction that is also going to help us? If, for instance, here, we assume that this thing that we have here is equal to 0, not only we have some restriction on u and v, but this equation also becomes simpler. And what will it be? It will be u to the power of 3 plus v to the power of 3. This term, this whole thing is now gone. It is equal to 0 because we are assuming that 3uv plus p is equal to 0. Okay, this is our assumption. And we have plus q equal to 0. Another thing that I'm going to do. U to the power of 3 plus e to the power of 3. What is this going to be equal to? Minus q. Okay. I want to also have u to the power of 3, v to the power of 3. Take this b to the other side, divide it by 3, and raise to the power of 3. So u to the power of 3, v to the power of 3 is going to be minus p to the power of 3 divided by 27. Is this clear? Okay. Now I have a question to ask you. If we have two numbers such that we know what is their summation and we know what is their multiplication, what are these two numbers? How can we find them?
Take the square of the multiplication.
Square root of multiplication?
Yeah.
If you take the square root of multiplication here, you are claiming that u3 and v3 are square root of this one? Check it and see if it is working or not. I think we need to do something else. if you have two numbers such that we know what is their addition and we know what is their multiplication, how can we find these two numbers? Dan, please go on. You have some idea?
I think we can write u plus v in parentheses over 3.
Okay.
We can also write with this, and we can find u and v.
Can you please give me explicit formulas for them?
Maybe make one subject of the formula and include it in the second equation, so it's like becomes 1.
Yes, exactly. We are going to put them inside an equation. But the equation that we are using is this. Like you're saying, they are the same idea, some kind of, but let me give it a formal thing. Look at this. When we are writing this x minus a multiplied by x minus b equal to 0. What is this a and what is this b? A is one root for this second order or quadratic equation. B is another root for this equation, right? But if you write this in the multiplied form, what we are going to get? X to the power of 2 minus a plus b times x plus ab equal to 0. What does this mean? Yes, if I have two numbers such that I have their summation and I have their multiplication, then these two numbers are actually the roots of this equation, this quadratic equation. And we know how to solve the quadratic equation, so we can find these roots. Okay, let's write this equation for these two numbers. If I want to write this kind of an equation for this one, what should we do? What is that equation? It is x to the power of 2 minus this number plus this number, which is going to be what? Minus q. So I'm just going to, instead of this a plus b, write minus q. With this minus, this is going to be plus q, x. What is their multiplication? As you see here, minus p cubed divided by 27. Okay? Now we have a quadratic equation, and we know that the roots of this quadratic equation are u3 and v3. Can you please find that roots? Yes, exactly. So let's go on with this. First of all, what is our delta here for this quadratic equation? Q squared plus
4 open bracket
4 times p to the power of 3 divided by 27, right? So what is our u to the power of 3?
No,
It is going to be
it's negative. Negative, not positive.
minus 4 times with this minus, right? We have a minus here. That is why when multiplied it's going to be plus.
There is minus.
Minus 4ac, right?
Yeah. Okay.
4
Yeah,
minus with this minus multiplied, minus down row plus. Fine? Okay. So what is our first root? What is our first root, which is going to be our x1, which is u3?
Q
Minus q
plus
square root.
square root.
The square root of this one,
Yeah.
which is delta, okay,
Over 2.
over 2a, which is 2.
Yeah.
And what is my second root?
Minus Q.
Which is v to the power of 3.
minus
Minus q
Minus
minus the square root of delta divided by 2. Okay? Now, from here, what is our u? What is our v? Our u is going to be the third root of this. Our v is going to be third root of this. What was our t if we have u and v? This one and this one. So our t is going to be, let me come write it here. So our t is going to be third root of minus q plus q squared plus 4 times p to the power of 3 divided by 27 2 plus cube root of minus q minus q squared plus 4 p2 27 divided by 2. Okay? This is called Cardano's formula. We are not going to memorize this. Not at all. Not at all. The thing is that we are just trying to also understand what is happening and why we need these complex numbers, and it is just for the case of understanding some things. We are never going to memorize anything in this course, so don't worry about it. Okay. What is wrong with this? No. What is wrong with this problem? With this solution of the equation?
It's too large.
How many? It is too large, yes, of course. But besides that, what do you see here again? How many roots we are expecting to have from a third degree polynomial equation? 3, right? Do you see the 3 numbers here? So is it wrong or what? The thing is that historically even, they have been trying to look at this equation, x to the power of 3 minus 15x minus 4 equal to 0. Okay?
When you do this using like the long polynomial division, there's a remainder. So will the remainder be like the last term that's missing?
Here, we are not doing any polynomial
The polynomial, right?
Here,
Yeah, like if you want to find the roots.
yes, if you can guess one of the roots,
Yeah.
you can do that long division and turn it into a linear term multiplied by a quadratic term, and then yes, definitely you can solve it. Yes, definitely. But sometimes for any cubic equation, we cannot guess that root. So we need to have a general formula, right? This is why we are doing this kind of things. The thing was that Cardano himself tried to use this formula for this equation as well. Okay? One of the roots of this equation is the number 4. Can you please check it? 4 to the power of 3, 64. Minus 15 times 4, 60. So there's 4, minus 4. So 4 is clearly a root for this equation. But the thing is that when you apply this equation, this formula, Cardano's formula for this, if I'm not writing it wrong, let me check it. I have it here so not to make any mistakes. Yes. You can see that this is 2 plus square root of minus 121 plus third root of 2 minus 121. Okay? And where is this number 4 here? Does it even not work for simple equations that we can guess their solution? If it doesn't work, so what is wrong with this? Have we made any mistake in our finding these things? First of all, why does it not work here? Where is this number 4 in this formula? And we are expecting to see 3 roots, but it seems apparently that we have only 1. So what is wrong with this? Bombelli has shown that this number is actually this one. If you do 2 plus I cubed, you will see that it is going to be 2 plus, what is this in our complex numbers language? I times 11, right? You will see that this is going to be I times 11, which is going to be this one. And this number here, this is equal to this one. And this one is here is actually 2 minus I to the power of 3. Okay? If you take its third root, what this is going to be? 2 plus I plus 2 minus I. 2 plus I plus 2 minus I is 4. So it is actually number 4. We have number 4 here. Okay, so it is working. But in order to be able to find this, we need to calculate the third root of a complex number, right? And now, question. When we were calculating second complex root of complex numbers, how many numbers did we have? 2. If we wanted to calculate the third roots, how many numbers did we have? 3. So yes, exactly. When we are calculating this third root, if you take it as complex third root, we are going to have 3 numbers here. What about this one? We are also going to have 3 numbers here. This is exactly like what we have been doing for finding the square root. We had x1 and x2, we had y1 and y2. 2 options for x, 2 options for y. It is again something like this. For this u that we are looking for, since we are taking the third root, we actually have 3 values, 3 complex roots, and for v also we have 3 complex roots, okay? Now also another problem arises. If for this value of u, we can select 3 values, and for this v, we can also select 3 values, how many options do we have in total? 9. Does this mean that we have 9 total different roots? We shouldn't have, right? You're expecting that at most 3 roots. So what is wrong with this, and how can we really come up with finding the true ones? The thing is that we had some additional expectation that we had imposed on this u and v, right? We said that let's select them in such a way that u and v is going to be minus p divided by 3. Do you remember this? Or 3 times uv plus p is equal to 0. This is going to help us to find the true ones that we can go with. For instance, let's assume that from these 3 roots, we are selecting one of them, and from 3 roots, we are selecting the other one. Let's call it u1 and v1, such that u1 times v1 is equal to minus p divided by 3. Okay? We select these options. What are my other options? If I want to write all of the third roots of this u, how can from this I get to the other roots? If you remember, we were just rotating them, right? And how much I need to rotate this? 120 degrees, 120 degrees, and 120 degrees, right? In order to come. But which number actually helps me to rotate a complex number 120 degrees? Not pi, but the third root of unity, right? What was the third root of unity? That minus 1 over 2 plus square root of 3. You see? So if I multiply this by this w3, which is the third root of unity, then I'm going to get the other option. And if I again multiply this with the third root of unity, which means that I'm just rotating now at 240 degrees, which I'm coming to the third option, this is going to be w3, u1. Okay? So 3 options for the roots are going to be like this. What about v1? You can also do this. w3, v1, w3, this is to the power of 2, this is to the power of 2. Okay? 3 options for the roots of u, 3 options for the third roots of this number, or for v. Okay? We said that this is one eligible choice. Okay? If that is one eligible choice, such that their multiplication is equal to minus p divided by 3, what happens to my first t? Our t1 is going to be u1 plus v1, such that u1, v1 is equal to minus p divided by 3. Okay? What is other options? if I select this one, W3U1, for the root of this number as the value of U, which one of them should I select? Can I select this V1? If I select this V1, what is the multiplication of this one and this one? It is going to be W3 times, or omega 3 times U1 V1, which is going to be omega 3 times minus P divided by 3. It is not going to be equal to minus P divided by 3. So I cannot choose this one. What about this option? If I select this one and this one, what is their multiplication? It is going to be W3 to the power of 2 U1 V1. Is it minus P divided by 3? It is not. It is W3 to the power of 2 minus P. So it is also not working. What about this one? If I select this one and if I select this one, what is their multiplication? This is omega 3 to the power of 3 U1 V1. What is omega 3 to the power of 3? This was the third root of 1, right? Which means that if you take it to the power of 3, it is going to be equal to 1. So this is actually 1. And now their multiplication is going to be minus P divided by 3. Which means that if I select this one, I need to select this one. So our second root is going to be root of unity plus, 3. The power of 2 V1. Similarly, you can argue that if you select the third one, we need to select that second one. Okay? And we have 3 roots for our equation. Fine? For quartic equation, I'm just going to leave it to you as a research problem. Okay? You can also find a Schoenhaus transformation again in order to get rid of this z to the power of 3 in this quartic equation, and then you have some tricks to do in order to find a formula involving this addition, multiplication, division, and taking the roots. This kind of formulas are actually called radicals. Okay, radicals. The thing is that can we find for any polynomial equation a solution in terms of radicals? For the 5th degree equation, Ruffini and Abel. This is the same guy that we have been talking about, Abelian groups and so on. It's the same mathematician. They have shown that for a quintic equation, unfortunately, we cannot write any radical that gives us the solutions of these equations. Okay? What about higher degree equations? If you have an equation of degree n for n greater than or equal to 6 or 5, can we find solutions for their roots in terms of radicals? For higher order equations, Galois was a French mathematician, died in a duel when he was 20 years of old. But what he has been able to do is that he some kind of said, and he studied actually this kind of symmetric structures and group theory and this kind of things. I'm not going to get into that. What he has shown that there is some relationship between the roots of a polynomial equation and its coefficients. These coefficients are actually symmetric functions of the roots. And if we want to have a solution for these equations in terms of radicals, some mathematical relationships must exist between the transformation of these things. Okay? And by studying these transformations, Galois has been able to prove that for equations that have degrees more than 5, we can never find any closed form formula or in terms of radicals. Okay? So if you have 6 degree polynomial equation, 7 degree polynomial equation, and so on, we can never find all of the roots in terms of radicals. And we need to do some kind of numerical approximation to this kind of roots and so on and so on. Okay? But again, let's go back to the same problem that we had. Can I write a polynomial equation like this: a0 x to the power of n plus a1 x to the power of n minus 1 up until an minus 1 x, an equal to 0. Let's assume that these coefficients are complex numbers. Okay, all of these. Can I always say that we can always find a complex root of this polynomial? Or can we say that, can we find the complex solution for this equation? Actually, if we are working with complex numbers, yes, we can. This result is stated as C is an algebraically closed field. What does it mean is this? If you take any non-constant polynomial such that has complex coefficients, you can always find the root for it in the set of complex numbers. And if you find that root, you can divide that polynomial, this equation, into z minus that root. You increase its degree with 1, then find another solution for that. Again, divide it by z minus that root, and now again you reduce the degree. And if you can do this, you can always find n roots for any equation that comes in this form. Okay? But do we have a general formula for this n roots? No. Unfortunately, we do not have a general formula to write them based on the works of Galois. Okay? But in the set of complex numbers, no matter what equation, no matter what polynomial equation you are going to write it, you are always going to find a root. What does this mean? This means that we are not going to extend again our number system to bigger number systems. C is already enough for us for solving all this kind of equations. Okay? One thing as a research question, let me give it to you, okay, which is related to this fact actually. It is called fundamental theorem of algebra. It states that any non-constant polynomial with complex coefficients has a complex root, has a root. Prove this. Can you find the elementary proof for this fact? Now that we are talking about this kind of equations, let me also tell you some other thing which may be interesting. Let's take this. Assume coefficients are real. Okay? What do I mean is that AIs are all real numbers. If you have a polynomial equation such that its coefficients are real numbers, and if you are able to find a root for it, which is a complex number. Let's call it z. If z is the solution of that equation, what will happen? It must satisfy this equation, right? So it is something like this. A1 z to the power of n minus 1 plus the rest a n minus 1 z plus a n equal to 0. This means that z is a root for this one, right? If for a polynomial equation such that its coefficients are all real numbers, if we can find a complex root, we can always say that conjugate of z is also a root for this equation as well. Which means that we can show that conjugate of z is also satisfying this equation. Which means a1 z to the power z conjugate a minus 1 plus z conjugate plus a n equal to 0. How can we show this? If I have an equation, a polynomial equation, such that coefficients are real numbers, and if we have a 0 for it, which is a complex number for this polynomial, or a solution for this equation, we can always say that its conjugate is also another solution. How? The thing is that, if you want to from this claim come to this one, let's take conjugate of both hand sides. If I take the conjugate of this one and this one, what will happen? What is the conjugate of number 0? 0. If we add two complex numbers to each other and take their conjugates, what will happen? It is exactly like taking the conjugate of two of them and adding them to each other, right? Because we had this formula z plus z prime r plus z plus prime r. What about multiplication of them? This is also true that we have this, right? So I have this complex number plus this complex number plus 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 plus. So what will happen? Can I say that I can take this conjugate on top of all of them? This one, this one, this one, and the rest? You can say that, right? I'm just adding these complex numbers. If I want to take the conjugate of the whole addition, I just need to take conjugate of each one of these and sum them up. Okay? Now, we have a multiplication here. What will happen to the conjugate of multiplication? We have conjugate of this one, conjugate of this one, plus conjugate of this one, conjugate of this one, and the rest. Okay? Now, this a0 is a real number. When we are conjugating a real number, what do we get? The same thing, right? The conjugate of real numbers are the same thing. So which means that this is going to be a0, as we have it here. Let me have it here, okay? Conjugate of this one is a0. What about z to the power of n's conjugate? Can I claim that it is conjugate of z to the power of n? Because n times we are multiplying z upon to z, n times, and I'm taking its conjugate. So it is going to be conjugate of z upon the conjugate of z, and we are multiplying it n times to itself. So it is conjugate of z to the power of n. Okay? So it is going to be this. And again, for the rest of things, I can write this, right? Now look at this. We have this polynomial equation which has real coefficients, and z bar is also satisfying this equality. What does that mean? It means that conjugate of z is also another root. So keep this in mind. Whenever we have a polynomial equation with real coefficients, and if you find one of the roots, which is a complex number, if you take its complex conjugate, that one is also going to be another root. Okay? Good. This is our whole case with the polynomial equations and this kind of stuff. Do you have any questions? Okay. We are done with complex numbers. Everything is done. If you research questions to you to think about them, then we are done. Do you know how our touch screens work? Touch screens, when we are having our phones that you're touching, how they are working actually? Baskı sensörü mü var orada? I don't know. Do research on it. But the thing is that in order to have the touch screen technology, we need to have capacitors. And in order to understand the properties of capacitors, complex numbers help us to understand them much more clearly, much more elegantly. So whenever you are touching your phones, you're actually using complex numbers in the real world. Okay? But there's this line, right? All of these developments are going back to 200 years ago. So we are actually talking about all of the things that happened many, many years ago. In order to be able to see the results and the fruits of this kind of thing, we need to follow that lines. One of them is this. Do a research on this and try to find out what is happening. Why these complex numbers are really helpful for us in this endeavor. Another research question. The model that I have presented you as the model of complex numbers was that R2, right? The plane. And for plane, each point of a plane, we have assigned a unique complex number and we have built our theory of complex numbers based on that. The thing is that we can also take a ball, the surface of a ball, and we can also uniquely, for each one of these points on the ball, we can also assign a complex number. This model is called Riemann's sphere, okay? And using stereographic projections, we can say that for any point on the plane of complex number, okay, we can uniquely assign a point on the ball. And we can also say that for some of the points in this sphere, actually the North Pole, we can also assign very, very far away complex points, which are called points in the infinity. Okay? Please do a research on this as well. What is the Riemann's sphere and what are stereographic projections? Okay? This stereographic projection has many applications in cosmology, crystallography, I don't know, in cartography and this kind of things. So please try to find one of those applications and try to find how they're related and maybe do a research on it. Okay? The other day we were also talking about something that I would like to also discuss it with you and also leave it to you as the research question 4. Are there any angle-preserving angle and area-preserving mappings between a sphere and a plane? What do I mean by this? maps are kind of maps that when you locally measure angles, okay, and you transform it to some other space, these angles are preserved. Locally you can go and measure the angles and they're going to be the same things. Area preserving mappings are the mappings between two spaces such that if there is this area, volume or whatsoever, after transformation this area and volume are again preserved. Okay? If you're looking for a sphere and if you're looking for a plane, is it possible to really find a mapping between sphere and the plane such that we can preserve both angles and both areas? The answer is no, actually. Have you ever seen our maps? You have definitely seen maps, right? Have you noticed that Greenland is almost as big as Africa? But normally, if you look at it, the area of Greenland is actually, I think Africa is 13 times or 14 times bigger than Greenland. Why is this happening? Why, as we go towards the poles, the countries are being bigger and bigger? Why? Can't we have a map such that the areas are preserved? The maps that we have is called the mercatorial projection, right? This guy was a merchandising. In our maps that you see, it is all of these Mercator's maps. And since in navigation it is important for us, if we have a device that shows us north, and we can take that direct line, and if we follow that direct line, we will go to north. We are some kind of preserving angles, right? And we need to know about angles in order to navigate these passes. So it is super important for us to preserve angles. Preserving areas is not that much important for us in terms of navigation. But the question is this: can't we have a map such that we can preserve both angles so we can use it in navigation, and also draw the countries in such a way that all of them have the proper sizes? They are not distorted. Is it possible or not? And the thing is that actually we can never do this kind of thing. It is impossible to have a mapping between the sphere and the plane such that both angles and both areas are preserved.